Okay, well, first of all, welcome everyone. Thank you very much for joining to this webinar. We must say, at least for Wupatec side, it's our first ever webinar. So we wanted in this webinar to bring together researchers, engineers, and industry experts to learn a little bit more about what is the FR3 band, why the hype behind it, why everybody in the world of wireless recently started talking about this, and what's coming next in the world of wireless communications. So a big thank you to Anis and Ahmed. They both come from the IEEE Young Professionals, together with the MTTS. They made this happen, so thank you very much. And thank you also for the speakers for showing interest in participating in this initiative. Without further ado, let's begin. So in this webinar, there will be 4 different speakers covering different topics. I will start with myself. My name is Irene. I work at Wupatec, and I am an RF design engineer. I will do a short introduction. I will explain what is the FR1 band, the FR2 band, and why we need the FR3 band. Then there will be Professor Sudarman Jayawira. He is a professor at the ECE department at the University of New Mexico, and he will cover the topics of academic research, standardization in the FR3 band, spectrum regulation from the US point of view, and auctions that are happening right now related to the FR3 band. Then there will be Aditya Dhananjay. He is co-founder and president of Pi Radio, and he will be talking about experimentation in FR3 band, spectrum sharing, challenges in software and hardware, and his solution that they deliver at Pi Radio. At the end, there will be Bethel Anya. He is a digital electronics and embedded systems engineer at Wupatec, and he will be talking about FPGA, RF SOC integration in this band, and he will showcase an amplifier measurement in the FR3 band through some results. At the end, there will be a session of questions and answers. So feel free to put the questions in the chat and we'll be more than happy to respond to them. So let's start with the basics. What is FR, first of all? FR stands for frequency range. Here's an image of the microwave spectrum divided by different wavelengths on the upper part and in frequencies underneath. We have from 300 megahertz to 300 gigahertz. There are different ways of naming the frequency spectrum. For instance, the 3GPP uses the names FR1, FR2. It is important to mention that FR3 is not officially designed yet, it is under study. And we have the blue circles underneath, that is the IEEE designation. And they use different letters from UHF to L band, S band, C band, up to VW, and so on and so forth. By the way, someone that I talked to last week, he's a microwave expert, and he made a statement that made me laugh, and I think it's true. And it's that there's no mnemotechnic rule to help memorize these letters. You just have to remember the letters by heart, and it helps for sure if you've been working in a specific project in a specific band that you will remember. All the information on the different frequency bands can be found in Chapter 5 of the 3GPP TS 38.104 specification. So I'm going to first explain the bands that are used today in 4G, 5G communications and why the scientific community, together with the industry, has started to look at the FR3 band. So the FR1 band, also named as the sub-6 gigahertz band, goes from 410 megahertz to around 7 gigahertz. It is today used for mobile networks, so 4G, 5G NR, for Wi-Fi, public safety and military, satellite communications, radar communications, and some IoT devices. Then we have the FR2 band, that is also called the millimeter wave band, and is another very known and used frequency band that covers from 24 gigahertz, more or less, to 71 gigahertz. Today, it is used for 5G high-speed data in indoor hotspots, fixed wireless access, so FWA. For those who are unfamiliar with the term, it's what connects a fixed location like a house to the internet using radio signals. So it's a wireless connection instead of cables. Then it's also used for automotive radar, satellite, and military applications. So the driving force behind why we should move to the FR3 band is the constant growth of data demand. So according to Ericsson, they released a report last year that states that in North America, monthly data traffic per smartphone jumped from 13 gigabytes, in 2021 to 20 gigabytes in 2022. And projections estimate that the traffic will be over 58 gigabytes in 2028. So this means that the data will have more than tripled in 7 years. So we have the current frequency ranges, the FR1 and FR2 that we use today, that are under pressure because they are either congested or don't support the current demands. So we have FR1 that provides robust coverage but limited bandwidth. This means that lower frequencies can travel farther, and this is practical for voice, messaging, and moderate data use, but it's not practical for high data rates. On the other hand, we have the FR2 band that provides high data rates, so super fast and low latency, but suffers from severe data loss and penetration issues. So this band would be ideal more for smaller areas. In the middle of both, we have the FR3 band. It's called also the upper mid band, according to some sources. And it goes from 7 gigahertz, more or less, to 24.25 gigahertz. And it's the middle ground. It's the sweet spot, as some people say. It is a part of the spectrum that is used. We cannot say it's empty. It's used for military communications, radar, and some satellite communications. Nevertheless, it is important to say that some segments are unused or available for sharing, and this has attracted the wireless industry. So the current scarcity of spectrum for communications is driving operators and researchers to look in this band, where they believe it is possible to coexist with the current users. What I mean with this is that since there isn't much spectrum left, the researchers and operators are now looking at this band, at the FR3 band, where they think it might be possible to share with the users that are already there. So what FR3 will offer is a balance between FR1 and FR2. It will offer a better propagation than FR2 and more spectrum than FR1. So this makes it attractive for medium range areas like cities, factories, and places with both indoor and outdoor coverage. But in order for the wireless industry to benefit from the FR3 band, regulatory frameworks, together with the scientific community, the industry, we all must adapt to accommodate for its use. So the FR3 band is said to play a potential key role by 2030. 2030 is the year when 6G will be commercially implemented, in theory. So different countries have already set focus on some segments of the band. So since some portions of the band are either partially utilized or can be shared, different organisms are now focusing their efforts on specific segments. So this time, I'll briefly compare the approaches taken by the United States, Japan, and the European Union, since these regions are home to most of today's audience. That said, it is important to keep in mind that countries like China or India also play a major role in the telecom ecosystem, and their developments are equally relevant. So in the United States, the more or less from 7 to 15 gigahertz range is under active study, with specific attention to the 12.7 to 13.25 gigahertz for potential commercial 5G. according to the NTIA. In Japan, the Ministry of Internal Affairs and Communications, so the MIC stated there, is examining the 7 to 15 gigahertz range to explore how satellite and mobile services might coexist. The European Union shows similar trends as the US and Japan and have shown interest in the under 15 gigahertz segment. We can all say that with all this, that countries agree on the fact that the 7.125 to 15.35 gigahertz range is gaining international attraction. Below 15 gigahertz, coexisting with existing services is more manageable, more feasible. Above that, there is still interest, but it's more conservative due to overlapping with radar, SATCOM, and defense systems that are currently using the band. All this doesn't come without challenges. There are challenges, of course. So hardwares must adapt to this band. We must develop the correct mechanisms of spectrum sensing, so to detect who is using this spectrum in order to share it. And we have to develop the security part for the signals to be protected against jammers or signal disruptions. So this is all I have to say from my side. And as introduced earlier, Professor Sudarman Jayawira from the University of New Mexico will now continue with the next part of the discussion, which is the academic research part, options, and standardization part in the FR3 band. I'm going to stop sharing the screen, and I leave you the stage.
All right. Okay. Thank you. Thank you, Irene. That great introduction. Well, good morning, good evening, good night, everyone, depending on wherever you are. So let's get to it. So the Irene gave a good introduction to FR3 brand and where it sits in with respect to the FR1 and the FR2 bands. And obviously the reason why we're talking about FR3 band right now is because of the 6G activities that are getting attention from all corners in preparation for the standardization activities that will happen in a couple of years. So with the 6G and in general next generation mobile wireless networks, there is the expectation of increased demand. And in particular in 6G, there are two usage scenarios that might require additional bandwidth and additional spectrum. One is the coverage. So the 6G ubiquitous coverage. So that essentially goes to acquiring the lower frequencies, because lower frequencies will propagate further, which will mean that it will provide you the additional coverage. On the other hand, the 6G also has the immersive communications. And those immersive communications, like the augmented reality, extended reality, or holographic communications over wireless links, could reach in excess of 1 terabits per second. And that would mean that you will need the additional bandwidth, but to provide the additional bandwidth or the additional capacity, you need the higher frequencies. So then you are looking at either lower frequencies for the coverage or the higher frequencies for the capacity or the bandwidth. But both FR1 and the FR2 are pretty much congested. But also the FR1, FR2 has the opposite properties when it comes to the bandwidth and the coverage respectively. So there sits in the middle the FR3 band, the roughly about 7 gigahertz to 24 gigahertz, and that has been attracting a lot of attention. Now, especially the lower FR3 band, the 7 to 15 gigahertz band is obviously the prime real estate for mobile wireless, because it gives the higher propagation as well as the higher bandwidths that are ideal for the mobile wireless. So for that reason, actually, that lower FR3 band is called the golden range of the spectrum for mobile wireless. So obviously, because of that, FR3 spectrum is considered as a candidate band or the candidate bands for 6G. And that actually started in the World Radio Communication Conference, WRC 23, that was held in Dubai in December 2023. In that, the WRC 23 agreed on IMT, International Mobile Telecommunications bands to be identified in the or the finalized in the WRC 27, which is mainly targeted for 6G. And those identified bands that are to be discussed in WRC 27 include both lower and upper mid band, depending on the different regions. For example, in the case of region 2, which include the North America, US, and Canada, primarily, those IMT identification bands are in the upper mid band, which is essentially FR3 band. And that, for example, include the frequencies from 7.125 gigahertz up to 8.4 gigahertz, as well as the 14.8 to 15.35 gigahertz. In addition, also in US currently, the frequency band from 12.7 to 13.25 gigahertz is also under consideration for 6G because it is currently undergoing the FCC rulemaking process. Now, whichever bands within the FR3 spectrum that are going to be considered for 6G or mobile wireless going forward, there is going to be the requirement for sharing with other existing systems, as Irene already mentioned. That is because FR3 spectrum has been used by various military communication and the military radar systems, as well as various satellite systems. For example, in US, the federal satellites operate from 7.8 gigahertz all the way up to 18.6, as well as 18.8 to again 20.2, and so on. And there are also non-federal satellites all in these spectrum bands as well. So the cellular concept essentially requires the spectrum to be exclusively allocated, because the cellular concept is not very flexible. It's not very amenable for the spectrum sharing and the coexistence. So there is the need to actually consider new technologies when it comes to the research, how to share the spectrum in these frequency bands if they were to be reallocated. Now, there has been more than 2 decades of work on dynamic spectrum sharing and cognitive radios, and using cognitive radios to do dynamic spectrum sharing. That has not really been successful in terms of the adoption in commercial systems. So maybe there is a chance with FR3 band because the operators and the next generation wireless will be forced to share the spectrum. For those some of those research that has been conducted in over the last couple of decades to be relevant when it comes to the FR3 band. I would also want to point out that the U.S. National Science Foundation and U.S. Department of Defense actually conducted or sponsored a workshop in software-defined radios for FR3 band, specifically last year, year before last year, in September 2023. That was actually held in Chicago. Now, you can find that workshop report, and that also talks about the need for FR3 band software-defined radios, as well as research that needs to be conducted, so that that can be conducted, that will help the innovations in the FR3 technologies if such a software-defined radio platform was available. The last thing I want to talk about is actually a little bit about the FR3 band, the spectrum reallocation and the auctions in the United States. Now, currently, there is a bill in U.S. Congress. The U.S. House of Representatives actually passed a bill last month, May 22nd, that proposed 600 megahertz to be released for the mobile wireless use between the 1.3 gigahertz to 10 gigahertz band. But that is spectrum. Exclude the 3.1 to 3.45 lower 3 gigahertz band, as well as the so-called 6 gigahertz band from 5.925 to 7.125. Now, because we know the 6 gigahertz, sub-6 gigahertz frequency spectrum is pretty much occupied, that leaves the potential to be in FR3 band, most of these 600 megahertz spectrum that House expect to be reallocated. Now, out of that 600 megahertz, there's expectation that within the first 3 years, the FCC should find somehow 200 megahertz to be released for the mobile wireless use. That bill is currently in Senate, U.S. Senate, and actually the U.S. Senate agreed, came to a compromise on that bill, and they actually increased that 600 megahertz to 800 megahertz. And the expectation, however, is that 7.4 to 8.4 gigahertz spectrum will be excluded from that allocation because of the interference to the military and intelligence service systems. So now that compromise, the 800 megahertz to be released for the commercial wireless use in these primarily FR3 frequencies will be reconciled and codified hopefully sometime within the next couple of months, because it's part of the reconciliation bill. So I think I went over a couple of more minutes than I expect, but I think I covered all the points that I want to cover. Thank you so much, and I'll pass on to Aditya.
Thank you very much. Very good insights. I remember I used the software defined radio report for some of my research as well, so it was good to listen to that. And now we will move on to some system level and tangible designs in this band, and we'll leave the stage to Aditya.
Thank you, SJ, and thank you, Irene. All right, so my PhD advisor used to say that experimental research is extremely important because most things work in simulations and theory, but very few things work in the real world. And so software-defined radios are as everybody knows over here, are the key technology that is used for experimental research. So Pi Radio is a small company. We are based out of Brooklyn, New York. And we got our start making software-defined radios in the millimeter wave bands. So we started off with a 60 gigahertz radio that had a 4-channel MIMO system. Then we built another system in the 57 to 64 gigahertz bands that had 8 simultaneously operating phased arrays. And then we also built an 8-channel fully digital beamformer in the 60 gigahertz bands. And so that's the kind of direction that we were going in. But a couple of years ago, one of our friends, Monisha Ghosh, who actually used to work at the FCC, told us, hey, why don't you go and build software-defined radios that operate in the FR3 bands, because that's where 6G is going to be. And given that Monisha Ghosh is 40 dB smarter than I am, obviously we had to listen to her. And so we also built software-defined radios in the FR3 bands, which is 6 to 24 gigahertz. I'm going to be talking about this. And the most recent thing that we've done is we're also building radios to operate in the Navy radar bands of 3.1 to 3.45 gigahertz to enable research for spectrum sharing for communications along with incumbent Navy users. So that's kind of an overview of what the company is and the kind of systems that we build. So let's talk about experimentation, the FR3 bands. Now, pretty much anybody who's done experimentation in wireless has either used a USRP radio or an RF SoC or a Pluto or any number of these software-defined radios that exist today that operate in the sub-6 gigahertz bands. These are amazing pieces of hardware, but the real power of these software-defined radios comes from the fact that there exists this universe of free and open source software that people can use to run their experiments. For simpler experiments, people can use GNU Radio, but if they want to run more complicated experiments with standards compliant 5G implementations, they would use things like Open Air Interface or SRS. So it is this combination of free and open source software with commodity hardware that has enabled research. But the big limiting factor is that most of these software-defined radios they operate in the sub-6 gigahertz bands, and they don't go up to the FR3 band. So what we did is we designed an FR3 add-on. So you can add on this FR3 front end to your existing sub-6 gigahertz radio, whatever your sub-6 gigahertz radio might be. And once you have attached our FR3 front ends to it, you now have an FR3 software-defined radio, and you can continue using pretty much the same software that you've been using at FR1. You can continue using it at FR3 with virtually no changes in the code required. So that's the idea behind what we've done. So the system in reality looks like this, the image on the left. So the yellow box over at the top is the Pi Radio FR3 front end. It has 2 transmit channels and 2 receive channels. And in this image over here, we have shown it operating with a USRP B210 that also has got 2 transmit channels and 2 receive channels. So you simply take the transmitter channels of the USRP, cable it into the Pi Radio board, and the Pi Radio system will upconvert the FR1 signals to FR3, and they get transmitted from the back side of this yellow box. And the receiver side is symmetrical, where the FR3 signals come in from the from the back side of the yellow box, and then we essentially down convert it to FR1, and the FR1 signals get cabled through to the USRP, and you are good to go, right? So the USRP does not even know that the signals are being hijacked and converted to FR3, but that's the idea. So you can use this with any USRP, any RF SoC, and so on. And in addition to the frequency up and down conversion boards, we've also designed and manufactured wideband Vivaldi antennas that can be used to operate all the way from 6 to 24 gigahertz. So this system, like the last thing I'll say about the hardware is that, yes, each of these yellow boxes is 2-channel transmit and 2-channel receive, but they can be tiled. So you can say, for example, put 4 of these yellow boxes together to get an 8-channel system that operates phase coherently. So that is, we've designed the system to have that ability. So in terms of the demonstrations that we've done, we actually did the world's first demonstration of 5G NR over FR3. We used Open Air Interface, and this was done in collaboration with Politecnico Milano. And then we have a collaborator, Allbe Smart in Portugal, really smart guys. They have this thing called the OAI box, and they have taken their OAI box, which operates in sub-6, and they've attached the Pi Radio board to it, and boom, now you have a G Node B that's operating in the FR3 frequency bands. In addition to that, we've also gotten UEs operating over FR3. So we've gotten it working with the soft UE from Open Air Interface, as well as commercial UEs based on a Qualcomm chipset. So again, just the same way you take a USRP, hijack the signals and upconvert to FR3, the same way you can take a commercial UE like a Qualcomm chipset, and then you can hijack those signals and go between FR1 and FR3. So that's kind of the set of systems that we have demonstrated over FR3. And of course, I'm not going to bore you with technical details about all the signal processing and stuff, so I'm going to move on. So the next thing that I did want to talk about is spectrum sharing. As SJ and Irene have mentioned, this is one of the biggest open challenges in wireless. Now, broadly speaking, there are 3 ways that you can do spectrum sharing. The first one is database-based approaches, where an incumbent basically writes into a database saying, I'm going to be using this spectrum at this time, so everybody else do not use it, right? So that is your database approach. The second approach is a newcomer can sense the presence of an incumbent and say, for example, if I'm a G node B, I can sense the presence of a Navy radar. And if I do, then I back off and jump to a different frequency, or I turn myself off, right? So that way I don't interfere with the incumbent. So these are the two broad approaches that are being spoken about. But there is a third approach, which is like true spectrum sharing, which is that if I am a G node B and if I sense the presence of a radar, what I should be able to do is I should be able to form a very deep wideband null in the direction of the radar, so that I don't get any interference from the radar, as well as when I am transmitting, I form a deep wideband null in the direction of the radar, so the radar does not get any interference from me. And so in this way, both the incumbent user as well as the new user can operate together at the same time in the same spectrum. Now, of course, doing this kind of true spectrum sharing requires beamformers that are capable of beamforming and null forming. And the beams and the nulls should not squint, and you should be able to control the directions of the beams and the nulls over a wide bandwidth. This turns out to be a fairly difficult problem to solve, from a hardware perspective. So in order to enable research in these bands, what we've done is we've built an RF front end that attaches itself to the Xilinx RF SoC, and this is just our first prototype of it. In fact, it's sitting on my desk behind me, and it operates from the 3.1 to 3.45 gigahertz bands. It's got a MIMO transmitter and a MIMO receiver with a self-calibrating RF front end. And this is critical because in order to do beamforming and null forming without squints, you need to do beamforming that uses amplitude, phase, as well as time delay. And so this needs to be calibrated in the hardware very, very, very accurately, an order of magnitude more accurately than present systems have ever required this to be done. So that's what we have designed. We have manufactured it, and we in fact got it back from the factory yesterday. So we are in the process of testing it, but so far it works well. It has not yet caught fire. So, we are quite happy about that. And the final thing I'll say about experimentation in these bands is you also need UEs that operate in these new bands. But if you were to use a commercial Qualcomm UE or a phone, right, these devices operate only in the standardized 3GPP bands as opposed to the newer bands that researchers want to operate in. So the final thing that we've done is we've actually designed and manufactured, and I have this as well on my desk behind me, a frequency conversion board that essentially can talk to a commercial chipset like a Qualcomm chipset and translate the frequency from a 3GPP standard band to something that is not 3GPP standard, so that it can be used for experimentation. And so, this is kind of the stuff that Pi Radio does. And let me just end by saying that our roadmap obviously includes, millimeter wave and FR3. But in addition to that, we have an ongoing DARPA contract to build MIMO software-defined radios in the 140 gigahertz bands. This is done in collaboration with Professor Mark Rodwell's group at Santa Barbara. Absolutely brilliant people. And then the other things that we are doing is we are working on the design of massive MIMO software-defined radios that are 64 channels or greater. This is something that really does not exist for the research community at any reasonable price point today. So this is something that we want to do. And so, yeah, we are always looking for people to team up with and collaborate with and go after, opportunities jointly. So I will stop talking now. And thank you.
Thank you very much. Very valuable hardware point of view. This is, without a doubt, the hardware part, adapting the hardware part is not an easy task. And the solutions that Pi Radio they have developed, it's amazing. So congratulations. Now I will leave the stage to Beta, that will show us another RF test-based solution with an amplifier measurement in the FR3 band.
Yes, thank you, Renee. So in order to not take much time during my presentation, I prepared a video for my speech. So let me share my screen. So hello everyone, I'm going to present the FR3 band in wireless communications in a digital perspective. So today we are going to focus on 3 major points. I'm aware that this webinar is dedicated to FR3 band, but it is very important to introduce our power amplifier test solution in FR1 band as it provides important context. It will be then easier for us to explore the evolution of the FR3 test solutions. And finally, we'll walk throughout a demonstration on the FR3 test solution from a digital perspective. So today, one of Wupatec solution is power amplifier design and digital integration. So to validate the power amplifier, a test bench is needed to measure the performances of the power amplifier regarding its output power and its frequency range. And we use the AMD ZCU 670 FPGA combined with our firmware to measure the RF PA in base station-like conditions. We also have a live selection of onboard DPD, digital police station. And for those of you who are curious to know more, here's a typical setup for our power amplifier measurements. So we can see on the left the demo board. It's an RF SOC DFE digital front end that integrates 8 transmitters and 8 receivers RF data converters for 7 gigahertz direct RF. And we only use only one transceiver to measure our power amplifier. So you can also see other equipment, other devices, and including a feedback path for data acquisition to measure fundamental parameters such as the EVM, the ACPR, and also on the right, a spectrum analyzer to visualize the output of the signals. And here is a graphic of available sample rates across the FR1 RF spectrum that we use with the FPGA demo board today. So we can choose any sample rate regarding the bandwidth of the signal we want to send. Provides a flexible live selection of sample rates covering the complete FR1 band. So I don't know if you listen, but Irene mentioned today earlier that many countries and most of our clients, most of our customers are interested in higher frequency, especially for 5G advanced in the 7 up to 15 gigahertz band, and we ought to meet the expectation. The problem is that the RF SOC DFE RF frequency doesn't cover the FR3 band out of the box. So we need to extend the RF frequency to RF using an intermediate frequency compatible with the RF SOC DFE. So then to the FR3 band that goes from 6 to 25 or 26 gigahertz. So after design and assembly, we obtain a complete prototype that you can see over here. So it's a plug and play FR3 band extension for AMD ZCU 670 that is capable of performing measurements in the FR3 band and meeting our customers' specifications and requirements. So both the sensor frequency and the output power are controlled by the FPGA firmware. And with this solution, we can cover the complete FR3 band and beyond. So from 6 to 26 gigahertz, while maintaining a relative high sample rate, enabling high-speed data processing up to 1.2 giga sample per second of instantaneous bandwidth, which is quite enough for any 4 or 5G signal test. And here is the demonstration of the FR3 band. So this is a screen capture from a spectrum. The spectrum measures the output RF signal in the frequency domain. And this test was carried out with a 5G signal test that occupies four channels of 100 megahertz at the central frequency of 12 on the FR3 band, and which allows us to obtain correct results in terms of linearity and dynamic range for accurate power amplifier measurements. So to sum up, we have seen our power amplifier test solution on the FR1 band and the evolution of the FR3 test solutions. And also we have reviewed a functional test on the FR3 band. Thanks for listening,